And the next thing is we are done with the Newton laws of motion, and we have to start this momentum. And the good thing about this is that most of it you are already aware of. This is the good thing. Okay, momentum is product of mass and velocity. Conservation, law of conservation of momentum, total momentum before and after collision remains same provided no external force act. Principle applied quantitatively to problems in one dimension, and every one of you is aware of this equation: m1 u1 plus m2 u2 equal m1 v1 plus m2 v2. So you're already aware of that. So we have to use these equations as well, and then we have to look for the types of the momentum, types of the collision. The collision is actually the interaction between two different objects, or it can be explosion as well. So it means that when two bodies are colliding, they can lose their energy or they cannot lose their energy. So that is elastic and inelastic. If the object is not losing its energy, it is elastic collision. If the object during collision is losing the energy in the form of heat and sound, so that is inelastic. So it means that the elastic collisions are actually the ideal collisions, and this inelastic collisions are actually the real life collision. Let's say if two cars are colliding, definitely you're going to hear their sound. So that's why we say this is inelastic. We will of course study them in detail. I'm just telling you about the basic things that you are already aware of in your metric or in your O levels. Okay, so this is the force which is equal to rate of change of momentum. And believe me, this is again a very basic thing. F is equal to ma, and you already know that we can write this a as v minus u over t, and then multiplying this m with both of these quantities. So this is mv minus mu over t. And what is this thing, mv minus mu? This is change in momentum. So that's why we say this is actually the O-level equation. Force is change in momentum over time. And then after this, the impulse, sorry, impulse is a change in momentum. This again you have done in O levels, which is product of force and time. Like if you multiply this time with this force, if you multiply them together, so you're left with the change in momentum, delta mv. So this is change in momentum. So then significance of area under force time, quantitative question, and these three things will be different for you. And these all things are your O level, and this is a brilliant thing that you are already aware of all these necessary topics. Okay, so okay, Ji. So as you know that we are already done with many of these things, not many, but maybe almost everything. Just few things are left in connection with the topic that we were doing today in the class. So actually we done till here, and now I have to tell you something about some more topics before going into the momentum. Okay, so here is an example for us. You can see that there are two masses. This is m and this is 2m, and which are connected through two threads. One is the yellow thread and one is the red thread. Okay, so these are let's say the elastic cords. Elastic cords mean that those are stretchable actually. Okay, so this whole system is at rest. Both the bodies are at rest. And what happened is that we cut this cord at point P. We cut it down. And after cutting this cord, what's going to happen is that this 2m is going to move down and this m is going to move up, right? So the question can be that you have to find the force and acceleration of both the masses. Like what is the force acting on both the masses after you cut the cord, and what is their acceleration? Okay, so first of all, we have to look for 2m. As you have cut the cord, so 2m is actually moving down freely. So it is in free fall. It is in free fall. and its weight is 2 mg, because weight is mg now, so its mass is 2m, so that's why it is 2 mg. So we say that the force acting on it is F equals to ma, and then as its m is 2m and its acceleration is free fall, which is g, so that's why we say that the force acting on it in downward direction is 2 mg, which is actually its weight. Like, this is a very simple thing. And what is its acceleration? Its acceleration is g. Its acceleration is g because it is in free fall. That's why the acceleration of this 2m is g. So I hope this is clear to you, that when you cut this string, 2m is in free fall because only the gravity is acting on it. There is no air resistance. It will be given to you in the question. So we will say that this 2m is falling freely. So it is in free fall, having acceleration of g and weight of 2 mg. Acha, next thing, what will happen to the mass m? Okay, this mass m was actually, its weight is mg, which is acting downward, and this tension T is the special thing, which is 3 mg. So why the tension is 3 mg? The reason is actually we have to go back to the previous slide. Over here, you have to mark the tension. And what is this tension equal to? Tension is actually equal to the applied force. So how much is the applied force acting in downward direction when 2m was there? It is actually 3m. M and 2m is 3m. And then what you do is 3m and then of course 3 mg. So the total weight downward in this position was 3 mg. So that's why tension in the cord is 3 mg. So this is very important thing. This is very important. This you need to know, that the tension is 3 mg, not mg. Why? Because the two masses are there. But once you cut the cord, the tension still remains 3 mg, but the downward weight becomes mg. So now as this mass is moving up, so we will say this F is equal to ma. And for the resultant force, as we discussed today in the class, as this object is moving upward, so we'll say, okay, this T is 3 mg and this is mg. So upward force is bigger, of course. So we say it is 3 mg and downward is mg. So 3 mg minus mg is the resultant force. And then this is the mass of this object which is moving. So this is 2 mg equal m. A, mm cancel the way. So A is equal to 2g. It means that this small m is moving upward with twice the acceleration value. It is moving upward with 2g. And then this is the tension. This is another proof that this is actually the force of the tension that I already told you, that this is equal to 2 mg plus mg, like weight of both the masses. So the tension acting is 3 mg. This was actually before that, before we use this equation. So this was the first equation in which we identified that how much is the value of T, and then we went over there to use F equal ma, and then we get that value. I hope this is clear to you. If anyone is having any doubt, then you may discuss this with me. Any doubt? Feel free to discuss.
Say gravity